Bismillahirrahmanirrahim. We start a new chapter in operating system and discuss concepts related to parallel processing. In this chapter, we'll be discussing how different processes are synchronized to work on a same resource one after another. In this chapter, process synchronization will be discussed and how process synchronization can be achieved and when it becomes a problem for the operating system. What are solutions for this problem and how your system can smoothly communicate, or how different processes within your system smoothly communicate with one another without involvement of operating system. So let's see the discussion agenda, the points that we are going to discuss in this chapter. This is the outline of discussion in this chapter. First, we need to develop a background with the term parallel processing. We will discuss what does this mean through different examples that you have already used within computers. So in order to develop the understanding with the topic, we need to explore different examples in order to make you understand what actually the term process synchronization or parallel processing means. Then, after developing a background on the topic, we will then discuss what is the critical section and why it is considered as a problem. What components within your system or within a process is considered as the critical section? What is the meaning of critical section and how it can create problems for the operating system? We'll be discussing that in detail. After understanding the critical section problem, we are then going to find the solutions. So we have different solutions for critical section problem. Some solutions are software solutions, while when we are using some hardware, so some solutions must be incorporated related to the hardware. So there are software solutions when you are using the software, for example, some code, or when you are using some application. So in that case, you will be using or you will be needing the software solutions if you face the critical section problem. So these two are the software solutions. Some algorithms being proposed by Decker, we will be discussing them, and then there is an algorithm that has been proposed by Peterson. So we'll be discussing both of them, their benefits and their drawbacks. And then the hardware solutions, as both solutions are provided. If the resource is a hardware, so you will have to implement the hardware solution, and if the resource is a software, so then we'll be needing the software solutions. After discussing the solutions for the critical section problem, then we will proceed another topic within process synchronization, which is a very important topic, that is inter-process communication. If you remember, when we were discussing processes chapter, that is chapter 2, so this was written or highlighted as one of the operations of the processes. This is the operations which normally a user or an operating system perform on processes. But inter-process communication is generally performed by operating system. That means how two or more than two processes communicate with one another without the involvement of operating system. So this is one of the operations being performed on processes. So your operating system provides some facilities or some resources to enable processes to communicate with one another. What are those resources or what are those facilities and how they are implemented? They have been implemented and you are using them, but we need to explore them in detail in this topic when we will be discussing inter-process communication. So inter-process communication is actually an operation being performed on processes that we have referred to in chapter 2, processes chapter, as one of the operations being performed on process. This operation is performed on by operating system on processes. So when two or more processes communicate with one another, so this sort of communication is known as inter-process communication. How this can take place? What are the facilities being provided by the operating system for different processes to make them enabled to communicate with one another? We'll be discussing that in detail. So this is the overall outline or agenda for this chapter that we'll be discussing in this chapter. So the first point or the first topic that we are going to discuss now is to develop an understanding with the term parallel processing or process synchronization. So we need to develop a background with the topic in order to move on to find the problems or the issues being created by process synchronization and how we can sort out this problem. So first we need to develop a background with the term process synchronization or parallel processing. Let's proceed with this discussion. In order to develop a background for the process synchronization, we need to understand the first point with few examples. The first point here says concurrent access to shared data may result in data inconsistency. Now, what does this point mean? Let's develop our understanding. For example, you might have used global data or global variables. Global variables are those variables which are available to all the functions, or they are shared among all the functions within a program. While the local variables are those variables which are only accessible to the functions in which they are declared in, and no other function outside of the one it is declared in can access it. Now, for example, we have two functions, function A and function B. Function A updates the value of global variable, while function B uses the value of global variable and performs further calculations. General rule of thumb says only one function at a time can access the global variable, so that all other functions can obtain the latest value of global variable. But if both functions A and B access the global variable concurrently, that is simultaneously, so what will happen? The result of one of the function will go wrong, as both functions access same value of global variable. While, as we just said, function A updates the value of global variable, so function B should get this updated value of global variable. But due to the simultaneous access to this global variable, both the functions receive same value, and hence the data or the output for function B goes inconsistent. Similarly, in case of hardware, since we have mostly a single instance of hardware in our system, so the hardware are also accessed in order or one after another. Let's consider the example of printer. If we activate printing for more than one documents, still the printing process will proceed in order. This will never happen that the printer will print half portion of all the documents, as this will bring inconsistencies for all the required documents. So it is important to access the shared resource in order, that is, one after another, in order to keep the data or results consistent. Resource, as you all know, can both be hardware and data, that is, software. So in order to maintain consistency, it is important to ensure the orderly execution of the cooperating processes. Cooperating processes are those processes which generally communicate with one another and then proceed their executions. If one process requires an resource on urgent basis, the other process then sacrifices for that one. So in this way, cooperation or inter-process communication can happen between processes and the work of different processes then proceed. So such processes are known as cooperating processes. While there are other processes who are competing processes. Competing processes are those who compete for the resources and want to avail the required resources earlier than other processes. So such processes do not sacrifice their demands for other processes. But in case of cooperating processes, processes communicate with one another through inter-process communication, and then data consistency can be ensured if the cooperating processes execute one after another or the execution of the processes are in order. After developing background with the topic, after having an understanding with the term parallel processing and how and why it is important for the system to work smoothly, now we have to move for the next topic, which is critical section and how it can be a problem. What is critical section and how it can bring problems for operating system? What are the conditions required to solve this problem? We'll be discussing that in detail in the coming section. Let's now discuss the problem of critical section. Critical section actually refers to the shared resource, both the hardware and the data. If we have to resolve the problem of critical section, we need to keep in mind few criteria or requirements for this critical section problem. So, critical section is actually that shared part of either software or the hardware. In hardware, for example, the printer is the critical section which is required by different processes, while the global data that we had just discussed as example in previous slide is the critical section that is being shared by different functions. So any solution that claims to solve critical section problem need to fulfill all these three defined criteria. The first requirement or the first criteria is the mutual exclusion. Mutual exclusion states that only one process can access critical section at a time, since critical section is a shared resource that can be either data or hardware. So if more than one processes are trying to access this critical section, even then only one process is granted access to critical section while the other process then has to wait. So you can see if you give command of printing for more than one documents, still the printing process will execute one after another. That means the printer will be assigned to single document at a time, no matter how many documents have been given the printing command. So this is what is known as the mutual exclusion. Second criteria is progress. Now, what is progress? Progress states if the critical section is available and there are more than one processes that want to gain access to critical section, so the decision to which process the critical section should be assigned must not be delayed or postponed indefinitely. This decision should be made quickly, and operating system makes this decision. The third requirement is bounded waiting. This actually means to interact or to treat all the processes equally. All processes should be given access to critical section equal number of times. If, for example, process A gains access to critical section 3 times, so process B should also be granted access to critical section 3 times. Otherwise, process B will face starvation. So any solution that claims to solve critical section problem must fulfill all these three criteria. If any single criterion or if any single requirement among these three requirements is not met, still that solution will not be considered valid or complete. So for any solution that claims to solve the critical section problem, that solution must need to fulfill all these three requirements, conditions, or the criteria for solving the critical section problem. After understanding what is critical section problem and why it is called as a problem, now we need to find solutions for this problem. So first we will have to consider the software solutions. What are the solutions being provided if you are using an application and face the critical section problem? So how you can cope with that problem? So we have software solutions in case you are using the code or the application. So the first solution within software solution is the Decker's algorithms. Different algorithms have been proposed by Decker. So we need to explore those algorithms and find out how the critical conditions for the critical section that we have already evaluated in the previous sections are being implemented in Decker's different algorithms. How they are implemented and what conditions are not being met. So we need to discuss different algorithms, as Decker algorithms are different in numbers and every single algorithm is not capable to fulfill all the three necessary criteria or necessary conditions that we had discussed previously for solving the critical section problem. So every algorithm is not fulfilling all the three conditions or all the three criteria. So that's why different algorithms have been proposed by Decker. So we need to explore one by one all of them. Now let's get to the solutions for critical section problem. We have both a software and hardware solutions as mentioned in the outline. For all the solutions, it is important that the three requirements that we just discussed in previous slide for the critical section problem should all be met. The requirements are mutual exclusion, progress, and bounded waiting. So let's discuss first the software solutions and check if all the three requirements are met or not. Decker proposed solutions for critical section problem, and that is a two-process solution. In its first algorithm, the use of turn can be seen. Here you can see the use of turn is visible. That means turn by turn processes can access critical section but not simultaneously. So if it's process I's turn to use the critical section, which is a shared resource, so the process J has to then wait for its turn. Now let's find out if the three requirements are fulfilled in this algorithm or not. The first requirement is mutual exclusion. With the use of turn, it has been ensured that only one process at a time would use the critical section and other process will have to then wait. That means mutual exclusion is being fulfilled. The second requirement is progress. As progress says, the decision to which process critical section should be assigned must not be delayed indefinitely. But here we can see if it's process I's turn, but I does not want to use the critical section, and it's not process J's turn, but J want to use the critical section. So unless and until I does not consume its turn, J will never get a chance to use its turn. So even though critical section is available and there is a process that wants to use the critical section, but still the decision to whom critical section should be assigned goes pending due to the use of turn. So process J may have to wait indefinitely in this case. Progress requirement is not fulfilled. I give you a simple example to this. Let's suppose we have a single multimedia and the use of multimedia has been scheduled as per timetable of your class. Now when it's my class with you, it's my turn to use the multimedia. But I do not want to use it for one single class, for example, and multimedia is available. If another teacher at the same time requires to avail that multimedia, he or she will not be granted access to that multimedia because it is scheduled to be in my use, but I am not using it. So other teacher will have to wait, which is not an ideal way. If I am not utilizing the multimedia, so that has to be made available to others, even though it is my turn to use it. I hope you have understood why the second criteria is not being fulfilled here. The third requirement is bounded wait. The use of a turn provides fair mechanism to treat all processes equally. The number of times process I is granted access to critical section, so that the same number of time process J will be granted access to critical section. So here bounded wait is being fulfilled. But since one requirement is not being met, so this algorithm is not considered a complete or a valid solution to critical section problem. Decker then proposed another algorithm in which the use of flag can be seen. Here you can see the flag, which is a Boolean variable whose value can be either true or false. Flag here means a signal, or simply you can say a signal to show wish of a process to use the critical section. When flag of a process is set, critical section will be assigned to that process and other process will then have to wait for its turn. After leaving critical section, a process has to set its flag off in order to let operating system know that critical section is now available. Now let's check all the three requirements in this algorithm. First requirement is mutual exclusion. Whoever process sets its flag first will be granted access to critical section first, and the other process will then have to wait. If both processes set their flags at the same time, then first come, first served policy will be imposed, but only one process at a time will acquire critical section. So here mutual exclusion is being fulfilled. Second requirement is progress. The use of flag has made the decision very simple. No matter which process is standing first in the queue, critical section will be granted to only that process whose flag will be on. So decision will not take long and progress is also fulfilled in this case. Third requirement is bounded wait. Bounded wait goes disturbed here because if only a single process requests critical section again and again by setting its flag, so one process may get more chances to use the critical section as compared to the other one. And fair treatment policy of bounded wait goes disturbed. So here bounded waiting is not getting fulfilled. After discussing Decker's solutions for the critical section problem, the next software solution being proposed is by Peterson. So now we need to discuss what is Peterson algorithm and how this algorithm can help to solve the critical section problem. This is our next discussion topic now. After multiple failed attempts by Decker, another solution was then proposed by Peterson. Peterson actually merged both the algorithms of Decker and make sure the use of both turn and flag simultaneously. So we are going to see his algorithm in the coming slide, but he made to ensure that both these variables must be used simultaneously, which has been done separately in separate algorithms by Decker. Now let's see how Peterson algorithm works. Let's see Peterson algorithm in this case. This algorithm uses both the turn and flag, and both the condition must be true in order to get the critical section. So here you can see the condition and is being used in the while condition. That means both the conditions, both the variables flag and turn need to be true in order to grant access to critical section. Again, it's a two-process solution. It states it has to be a process turn and its flag should also be set. Only then critical section can be granted to that process, otherwise not. Now let's check the three requirements. First requirement is mutual exclusion. This is fulfilled clearly, as at a time there has to be only one process turn. Even both the process may have set their flags, but the critical section will be assigned to single process at a time, the one whose flag is set and its turn is to use the critical section. Second requirement is progress. Use of flag simplifies the situation. If both processes are waiting for critical section, the decision as to whom critical section should be assigned can be made quickly. The one whose turn is to use the critical section and its flag is also set will only be eligible to use the critical section. So again here progress is getting fulfilled. as decision is being made very quickly. The third requirement is bounded wait. Bounded wait is also getting fulfilled with the use of turn. The number of time process I will use the critical section, so same number of times process J will get the chance to use the critical section. Hence, Peterson's solution is considered valid and exact or complete for the critical section problem. I hope both the solutions must be clear to you. That is all for now. In today's discussion, we started a new chapter, parallel processing or process synchronization, in which we discussed different concepts related to parallel processing. First, we developed a background with the term parallel processing or process synchronization using different examples. As we had said, that concurrent access to some shared resource, the resource can be hardware and it can be software. So concurrent access, that means simultaneous access by different processes to a single resource, may result in inconsistency of the data that is being operated by different processes. So we have seen this statement and we have seen the examples we have implemented this statement on both the softwares, the code, and also on the hardware. So why it is important to have process synchronization or to achieve parallel processing among different processes. Then we discussed the critical section and how it can be termed as a problem. Critical section problem need to be addressed on priority basis. If your system is facing critical section problem, so there has to be the solution. Whatever the solution is, the solution needs to fulfill 3 criteria that we had set for the critical section, for solving the critical section problem. First is the bounded waiting. Second is the mutual exclusion. And the third criteria is the progress. So these 3 necessary conditions need to be fulfilled in order to solve the critical section problem. And then we discuss the solutions being proposed to solve the critical section problem. 2 types of solutions are there. If you're using software, so there has to be software solution, and if the problem is being faced on hardware, so hardware solutions and need to be integrated. In today's discussion, we discussed the software solutions. 2 types of algorithms have been proposed, one by the Decker and another by the Peterson. We discussed how these algorithms fulfill or cannot fulfill the conditions being met for the critical section problem. So Peterson's solutions fulfill all the 3 necessary conditions being proposed for the critical section problem to solve the critical section problem, while Decker's solutions still have some ambiguity. Some conditions are fulfilled while others are not. We'll proceed with this discussion in the coming lecture, and we'll see how the hardware solution is implemented using some hardware. That is all for now. I thank you all.